Hello everyone, welcome to the third of these online supplementary lectures. We've completed our pre-study of vectors with regards to mechanics now. We're going to move on to calculus, which is the next aspect of mathematics that we're going to need to be doing in order to progress our understanding of mechanics. So let's dive right in. So last session, we did vectors and we did the cross product. So we did what the cross product is. And then we looked into like the general use of scalars and vectors in physics. So what has units, what has direction, what has size, where are these things important and why, what physical quantities need scalars and what ones need vectors. So now I reckon you should be able to use vectors to represent physical quantities where necessary. And as you do more and more physics, more and more quantities will come up that will either need vectors or scalars. Some might even need matrices, but we'll get onto that in a few years. And you'll also be able to perform these basic vector operations. So addition, basic stuff, subtraction, multiplication by scalars, division by scalars, but also the dot product and the cross product being probably the most conceptually difficult one. But I reckon you should be able to do it just using the rules that we've learned up to now. But now we're moving on to calculus. So what are we up to here? So we're going to learn or recap an intuitive understanding of what differentiation is. So we're not just going to use it as a tool. We're going to understand, well, we are going to use it as a tool, but we're going to understand where it comes from, how it's derived, and why gradients of graphs are so important in physics. That's the second one there, why differentiation is useful in physics. We're also going to get a bit of an intuitive understanding of what integration is. So you might know that integration is the opposite of differentiation, the inverse operation, but we're going to intuitively understand what we're doing when we're integrating, and crucially why it's the opposite of differentiation. So why is it that when I integrate a function I get the area under a graph, but also somehow integration is the opposite of differentiation? Why is that the case? We're going to prove that, and we're going to look at why integration is useful in physics, just like differentiation. If that's going to be useful, integration, the opposite, also probably going to be useful. Turns out it's useful in very different ways. And finally, how to calculate derivatives and integrals of general functions. So that's going to be the important bit, the using this thing as a tool. So by the end of this, you'll be able to perform differentiation and integration on basic functions, so like polynomials, x squared, x cubed, x to the power 4, blah, blah, blah. Exponential functions, so e to the power x, e to the power 2x, 4e to the power 2x, exponential functions. Trigonometric functions, sine, cos, maybe tan. Going to learn that too. And there's additional functions as well. You can go out and learn how those work. We're going to actually learn a method in this session to calculate the derivative of any function that you come across. So that's going to be useful. And we're also going to do some performing differentiation and integrals on combinations of functions. So these will be things you've come across before: chain rule, product rule, integration by parts, integration by substitution. The proof of these things is pretty long, so I'm going to leave it to the Maths 1 team to prove those things to you: the chain rule, product rule, integration by parts and substitution. But we're going to use them here to do some tasks, just to get ourselves back into the habit of doing a bit of calculus. So let's dive right into differential calculus, right? What on earth is it? What are we doing? Why do we care? Right. So if physics is about the measurement of physical phenomena, which it is, and the prediction of those events at a later point in space or time, i.e. sometime in the future, over there, what is this system going to look like? Does it not make sense that rates of change of these things in space or rates of change of these things in time are going to be at the core of all modern physics, right? If something changes over time, then how fast it changes over time is going to be really important. And that is what the gradient, or the time derivative is, the gradient. Equally, if something changes in space, temperature maybe, something's hot here and cold over there, how that temperature changes through physical space is going to be important, because it'll tell us about how that thing changes. And temperature moves around, energy moves around, things change, and that's going to be really important. We'll see moving forwards that there's something called a partial derivative as well, where you can change in both space and time in the same function. You can deal with those things in parallel. So that's going to be really important. But for now, let's just worry about changing in space or time independently. So let's dive right into the theory behind this. Here's a graph. Could be any graph, right? It looks something like an x cubed graph. It's got one up and one down. But in principle, it could be absolutely anything. And at the bottom there, you can see I've called this function z. And I'm saying that z is a function of x. Okay? So that's function notation down there. Z is equal to a function of x, which means that we can put x into this function and get out some z. And here's x, the x-axis. This function is z. I'm not going to call this axis z because we might have more than one function on this axis, but we could call this axis z, seeing as there's just one function on it at the moment. So what we can do now, maybe, put 2 points on it. Why not put 2 points on it? Here is z at a position x1. So here's x1, down here somewhere at a 7 point something. Z at x1 is that point, and it's going to be something like 7 point something, 6 point something here. And here's another one, right? x1 plus delta x, I've called it. So we'll see why that is in a minute. If this is x1, then that's delta x along. Z, open brackets, x1 plus delta x. It's going to bring us to here. We can get the gradient between these 2 points, right? We can draw a straight line between those 2 points. And that, naively, is the gradient between those 2 points. We obviously can see that this curve is extremely bendy, so maybe that's not a good representation of the gradient, but we'll be able to move forward such that it is shortly. So we'll draw this straight line between these 2 points. And that means we can put on a delta x here, right? So that's x1. That's delta x. So this is x1 plus delta x. Here then we've got z at that point and z at that point. So is this not also a delta z, where that delta symbol just means a change in that value? Change in x, change in y. And if we want the gradient between these two things, we might know that it's the change in z over the change in x, the change in the y-axis over the change in the x-axis, or in this case, change in z-axis over change in x-axis. So I've called that a finite change, right? That's why I've used this capital delta, Greek letter delta, the capital there. That means a finite change, as in it has a fixed length that we can measure. Delta x there starts off at 7 and a bit and goes up to 11 and a bit, so it's going to be 4 and a bit. Z here starts at 6 and a bit and goes up to about 9, so that's going to be about 2.9, 2.8 or something like that. And so from there we can calculate the gradient, right? Delta z over delta x is z2 minus z1. Delta x is x2, the second point, minus x1. And so we can change that now, right? Z at x2 minus z at x1 over x2 minus x1. And we can then add in that delta x to make it a bit easier. x2 minus x1 is delta x, it's defined that way. Z is now x1 plus delta x and x1 there. Because if x2 minus x1 is delta x, then x2 is x1 plus delta x. So we've now expressed this delta z on delta x in terms of delta x and a single point on that graph, which is what we want. This is where we're going with this. And this is a finite change, right? But we can see that if delta x is too big, we miss out all this stuff in between. Imagine that x is some sort of motion, right? How far is it moving in the x direction? And z is how far is it moving in the z direction. So this is something like a path. Imagine someone running along this path. We're looking down on them from the top and someone's running along this path. If we said that this was representative of that motion, we'd be missing out the fact that they changed direction and then changed direction again before they got there. We're making we're missing out all that in between stuff. And especially if we're doing physics, we don't want to miss out that in between stuff. We want to get as accurate as possible at every single point across that path. So how can we do that? Well, this is where we change from a finite change, delta x, to an infinitesimal change. And this is the key behind calculus, because here, by taking a measurement of a position here and taking a measurement of a position here, the best we can do is approximate it as a straight line, right? Gradient being delta z on delta x. But we don't want a straight line. We want to capture that entire function. And so here's what we do. We define, again, we're defining this. We're inventing calculus, just like Isaac Newton and Gottfried Leibniz did, roughly at the same time. We're going to invent this mathematical tool in order to do the physics that we need to do. We're going to say that dz by dx, which is just a notation, the derivative of this function z with respect to x is equal to the limit as delta x tends to 0 of delta z on delta x. So what does that mean, this idea of a limit? It's the limit of this function as delta z and delta x tend to 0. Well, what that means is we're going to take delta x smaller and smaller and smaller, and as we do that, delta z is also going to change. It's going to change as delta x goes down and down. Delta z is going to change as this graph moves through this graph. So here's delta x. As delta x gets smaller, we're going to move along the graph z of x, and that delta z is going to change as we do this. And the limit as delta x tends to 0 is what this line looks like as that point comes on top of that point. That's what the limit is. Because if we just set delta x equal to 0, we'd get 0 here. We'd also get 0 on top. 0 divided by 0. That's not going to be good for us. So we're not setting delta x equal to 0 here. That's not what we're doing at all. The limit as delta x tends to 0 means we're looking at the behavior of this line as that point approaches this point, moving along this graph. What does it look like? And so we can put delta z and delta x in there. Z at x plus delta x minus z at x1, so that's delta z, over delta x. And we can just get rid of that x1 now, because x1 is nothing special. x1 could be down here. x1 could be up here. x1 could be literally anywhere. It doesn't matter. So we'll just get rid of that subscript and say that dz by dx at any point x is defined as the limit as delta x tends to 0, as this point approaches this point along this graph, of z at x plus delta x minus z at x divided by delta x. And that's an expression of the gradient as that delta x gets closer and closer to 0. And so we want the rate of change over the smallest possible region, right? That's what we're going for. So let's look at what happens if we do that. Delta x is changing. Delta x is now in the other direction. And as those 2 points go on top of one another, we see that that line hasn't disappeared at all. It's got closer and closer, to the tangent of that graph at that point. And that is what the derivative of a function is. The gradient, the tangent of the curve at that point, where delta z is equal to 0 and delta x is equal to 0. The limit as delta x tends to 0. So let's do that in practice. Let's express some functions mathematically, keeping that graph in mind, and see what happens. Let's do a polynomial. A polynomial, z of x, so it's function z of x, is equal to ax to the power n, where x is our variable, a and n are constants. So this could be x squared, x cubed, x to the 4th, x to the 5th, x to the 6th. imagine x squared in your mind right now. 2 different points on that graph. One at z x plus delta x and one at z at x. And imagine that delta x between them. Draw it on a piece of paper if you want. We want to calculate the derivative of this function. So we've got z at x plus delta x minus z at x divided by delta x. It's going to be the tangent to that curve at some point x. That's what we're going to get. So let's substitute in this function, right? Z of x is ax to the n. So z of x plus delta x is ax plus delta x to the n minus ax to the n divided by delta x. And we want the limit as delta x tends to 0. Can't set delta x equal to 0 right now because we'll get 0 on the bottom and that makes no sense. We're not trying to get a 0 on the bottom. We're trying to take the limit as delta x approaches 0. That's something very different. So let's expand the mathematics of this and see where that takes us. This ax plus delta x to the n can be expanded using the binomial expansion. So if you've come across that before, great. If you haven't, get on Wikipedia. But this x plus delta x to the n is x plus delta x times x plus delta x times x plus delta x times x plus delta x n times. And timesing out those brackets has a certain pattern to it. And that pattern is expressed here. So a is just a prefactor, it doesn't matter, it comes out the front. Open brackets. First of all, x to the n, because if you imagine n lots of brackets, there'd be an x in each one. So x to the n. And then n delta xx to the n minus 1. So we get n lots of that term. We get a half nn minus 1 lots of delta x squared x to the n minus 2. The binomial expansion is a lot easier to do if you write it out on a piece of paper and understand how that works. So if you've not come across the binomial expansion, put it into Wikipedia, have a look at what it is, try and times out some brackets that look like x plus delta x to the power 3, to the power 4, and see what the pattern is. You'll see that this pattern is true for every n. And it goes on and on and on and on and on until at the other side we get delta x all to the power n. So it keeps going until we get delta x all to the power of n. Close that bracket. And then we're minusing z of x still. So we're minusing ax to the n, dividing by delta x, dividing by delta x. So all we've done is taken that x plus delta x to the n and expanded it like this. So now what we're going to do is times out the brackets a little bit and cancel some terms. So I've got an ax to the n there, ax to the n there. So that term and that term are going to cancel. And then we can do the rest of it. So we've got n delta x minus 1, blah, blah, blah. That keeps going all the way until the end. So all we've done is taken that term there and cancelled it with that term. So it's gone there. Divide by delta x. Well, now there's a delta x squared here, a delta x here, a delta x cubed in the next one, a delta x to the power 4 in the next one, blah, 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 blah. Let's cancel those delta x's. What have we got now? Well, that delta x is gone. So we've got nx to the n minus 1. That delta x is not squared anymore, but it's on its own. Next delta x will have 2 instead of 3. The next delta x will have 3 instead of 4. We've lost a delta x from every single term. But now we don't have a delta x on the bottom. Setting delta x equal to 0, or allowing this function to move towards delta x equals 0, is no longer a problem. We're not going to get anything that's mathematically tricky, like a divided by 0. So now we can just set this equal to 0, and the next term, and the next term, because every term after this one is going to have a delta x in it, and that's going to get set to 0. So that term goes, every term except the first term goes, and we find that if we take that limit, the gradient of ax to the n is anx to the n minus 1, or bring down the power and take 1 off the power. That's the famous formula for a polynomial. So there we go. That's the first one. That's the theory behind calculating derivatives of functions. And you can do that for any function Any function that you can make an expansion of by either what's called the binomial expansion or other forms of expansion like trig functions expand and things like this. You can use this method to calculate the gradient function. So for any point x on a graph, the gradient at that point, dz by dx, is equal to this. Nice. So now we've got task 1, right? Differentiating common functions. So this one's a bit tricky. It's also technically optional. You don't have to do it. If you're not interested in the maths, you can just take my word for how to take derivatives of functions. You can just learn them by rote. But if you're interested, what I want you to do is use the general definition of the derivative to show that if a function p of x is equal to pm sine kx, then the gradient dp by dx, or the derivative dp by dx, is equal to pm k cos kx, where p subscript m and k are just constants. That's all they are. They're just constants, no problem. The second one is if x of t, some function x, which is a function of t, is equal to a e to the bt, then the derivative, or the gradient, dx by dt, is equal to b a e to the bt. So all we've done is bring down that b, where a and b are constants, t is the parameter, and e is the exponential function. So that, I reckon, if you have half an hour on each one, give each one a real good go. Take half an hour on both of them, if you're interested. If not, I'll go through them here. So take about half an hour on both. That's the general definition of the derivative, by the way. Okay, I'm going to go through these now. So here we go. If p of x, I hope that, by the way, if you did go away and have a go at those, these are supposed to be hard. Don't feel disheartened. These problems are hard because they really make you think about what that function is. By setting these problems, I'm really making you think about what a sine function is, what it means to take a derivative or get the gradient of a sine function. You might have had that function in mind with 2 points on it and trying to look at what the gradient looks like as those points come together. Let's start with p of x equals p of m sine kx. So we want to take that general form of the derivative again. So that general form of the derivative is the function at x plus delta x minus the function at x divided by delta x. Doesn't matter that before it was z and now it's p. Doesn't matter, it's all just symbolic. We can use whatever symbols we like. That's going to be important as you start to do different areas of physics. But we can use absolutely any symbol we like. So dp by dx, let's substitute that sine function in. So p at x plus delta x is pm sine, open brackets k, open brackets x plus delta x. So it's not kx, it's kx plus delta x, because we're replacing that x by x plus delta x. That might tell us that we're going to have a double angle formula coming in here, right? Minus p of x or minus pm sine kx divided by delta x. So our goal here, just like before, is to do our best to get rid of that delta x as best we can. That's our goal. So let's expand it out. So sine of kx plus k delta x, well, that's the double angle formula, isn't it? And we can take that pm, that's a constant by the way, we can take that to the front of everything. So pm sine kx plus k delta x is sine cos plus cos sine. That's the double angle formula for sine of a plus b. It's sine a cos b plus cos a sine b. In this case, sine of kx cos of k delta x plus cos of kx sine of k delta x minus sine kx. That's interesting. We've got a sine kx here. We've got a sine kx here. Let's factor it out. So if I take sine kx out, and pm, by the way, take pm out the whole lot, because pm's not going anywhere as delta x tends to 0, so you can take it out of the front of everything just to clear everything up. We've got cos kx, lots of sine x, kx, and we've got minus 1 lots of sine kx. So if we factor out sine kx, we've got cos kx minus 1 plus cos kx sine k delta x over delta x. That's what we've got. So we've got these two fractions here now. I'm going to rearrange that a little bit because I want all my delta x's together. So I'm going to put this fraction at the front and I'm going to put that fraction second. And I'm going to bring that cos kx down the front. I'm going to bring that sine kx down the front. And I've turned around 1 minus cos kx to pull out that minus sign there. So I've got cos kx, sine k delta x on delta x, minus sine kx, 1 minus cos kx on delta x. There. Here's the trick. I'm going to multiply here and here by k. And I'm going to multiply here and here by k. And then I'm going to take that k out the front because it's just a constant. So now I've got sine k delta x divided by k delta x. I've got 1 minus cos k delta x minus k delta divided by k delta x. If you were to put this into your calculator, sine something over something, and make that something smaller and smaller and smaller and smaller and smaller and smaller, you would find that this fraction actually tends towards 1. It's called the sinc function, sine c. Sine of something divided by that thing has a peak right in the middle where it equals exactly 1. And so that means as we take the limit of k delta x going towards 0, which is the same limit as delta x going to 0, it just goes to 0 at a different rate. If we take the limit as k delta x goes to 0, then this term, this fraction becomes 1. Whereas 1 minus cos kx on k delta x, well, let's think about what cos k delta x does as that k delta x gets closer and closer to 0. Cos is going to go to 1. 1 minus 1 is 0. 0 divided by 0. This one actually decays towards the value of 0. And you can put that in your calculator to find out why that is. So this one goes towards 0. This one goes towards 1. So that means that as we take that limit, that entire term goes away, and that becomes 1, leaving dp by dx is pm k cos kx. And that's our answer. That's what we wanted to show. So that last little bit might have thrown you. That bit you might have got stuck at that little bit. That's absolutely fine. I just wanted you to think about what these functions do as that value gets closer to 0. So don't be disheartened if you didn't do that k delta x stuff. Don't worry about it. If you just put numbers in your calculator to see what it looks like as it got closer and closer to 0, that's absolutely fine. That's one way of doing it. But the mathematically rigorous way of doing it is this. If you wanted, you could do px equals pm cos kx and prove that it equals minus sine using exactly the same arguments I've made here. Exactly the same. So sine goes to cos, cos goes to minus sine. You can prove that if you want. So let's do the next one. Same thing. X of t is ae to the bt. Let's substitute that into the limit formula. This is the general form of the derivative again. Different variables, but it doesn't matter. X as a function of t plus delta t minus x of t over delta t. Delta t is getting closer to 0. Let's substitute in that exponential function. E to the bt plus delta t minus ae to the bt on delta t. A can come out to the front because it's a constant. E to the b t plus delta t, well, that's equal to e to the bt, e to the b delta t. Factor out that e to the bt and take a e to the bt outside the limit, because t isn't going anywhere as delta t changes to 0. Delta t is its own thing. It's its own separate thing. So that can all come out. Now we've got dx by dt is equal to a e to the bt. Limit as delta t tends to 0, e to the b delta t minus 1 divided by delta t. And that is as simple as we can get this. So how are we going to take it such that delta t tends towards 0 if we've got a delta t on the bottom? We don't want to get something divided by 0. That's got to be annoying. We don't want that. And if we do e to the b delta t, where delta t is 0, that's going to be 1. 1 minus 1 is 0. 0 divided by 0. It's not good if we don't know how the functions behave. We can do the same trick as we did before, as we let this and this get smaller and smaller and smaller and smaller and smaller and see what this limit becomes. You can do that if you want. But first thing we need to do is multiply b here and b here, just like in the sine example, so that we have the same thing at the top and at the bottom, because we want this and this to be the same in order to take limits properly, because this and this need to decay at the same rate. So we put b delta t tending towards 0 in the limit as well. So now we've got this thing. It turns out that the definition of e, as in the number e, the definition of that number, how it's defined, e is the number such that the limit as epsilon tends to 0 of e to the epsilon minus 1 divided by epsilon is equivalent to 1. That's the definition of the number e. And that comes from how e was developed. It's to do with compound interest and how things change when they grow based on their previous value. So you can think about money in the bank with an interest rate, although interest rates are a bit crap at the moment. You can think about it in terms of interest on interest on interest on interest. This was where e was developed from. And it was defined such that this is the case. And here we can see e to the something minus 1 on that something, limit as that something tends towards 0. Well, if that number is e, then this has to be 1. This has to be 1. E is defined such that this is 1. And if you put any numbers you like in your calculator for b and delta t and let it get closer and closer and closer and closer to 0, you'll see that this becomes 1. Because e is defined that way. Any other number doesn't work. E is defined this way. And so what that means is that this becomes 1 when we take that limit. And so dx by dt is ba to the e bt. So again, that's another little trick there. So these derivatives, these things that we use quite often, it turns out that to do these calculations, to calculate derivatives, we have to have a real understanding of what these functions are, right? How they were developed and stuff like that. So I hope that calculating these derivatives manually, although difficult, gives you a bit of insight as to why it's really important to understand what a function is when we're trying to take its derivative. However, if you want to remember all the basic derivatives off by heart, go for it. The derivative of sine is cos. Cos is minus sine. If you've got something in that thing, if you've got cos kx, you take the k out. If you've got sine kx, you take the k out. Exponential function, you just take that power and bring it straight down, or the prefactor towards that t, you take it and bring it straight down. If you've got a polynomial, you take that power and then minus 1 from the power. These things you can just memorize. But if you really find the mathematics interesting, then go through these derivatives, understand how the functions work, and derive these derivatives for yourself. So we've done derivatives now. So let's move on to integration. Opposite of differentiation. Opposite in that if we've got a gradient function, dz by dx, then integrating that function should give us the original function back. That's what integration is. So we can just think of it as the opposite of differentiation. Every derivative we've learned, sine goes to cos, cos goes to minus sine, we can just do the opposite in order to integrate. That's one way of doing it. But again, if we're doing physics, if we're doing this thing properly, we want to have this intuitive understanding of what these things are. So derivatives are gradients. They're the gradient of a function at a specific point. The tangent. Well, it's the gradient of the tangent line to that function at that point. What's integrals then? What is an integral? What is integration? What's the intuitive understanding of this? Oh, yeah, here's why we're not doing physics yet. It's the opposite of differentiation. If rates of change in space and time are important, then surely the cumulative effect of all those changes over space and time are equally important, right? So if we've got a rate of change of something, we want that rate of change at every point. That's the function itself. So the opposite of differentiation is going to be as important as differentiation itself. And in lecture 1 mechanics, we'll see that immediately. So we'll start off with speed, we'll start off with acceleration, and we'll get speed and we'll get distance, or we can start off with distance and get speed and acceleration. Differentiation or integration, both of those things are as important as the other, and we can start wherever we like. So differentiation is important because rates of change are important, then integration is also going to be important. So what's the theory behind it? Here we've got a curve. Again, it could be any curve, but I've drawn like an x cubed thing. It's a bit more stretched out so we can see things a little bit easier. X here. This function is z of x. So we now know that dz by dx at some point is the gradient of this function. dz by dx is the gradient of this function. But what I want you to think about now is if we're at position x here and we go up to the line, that point there is z of x, right? It's the point z corresponding to that point x on this graph. So let's put a little delta x along this graph. And instead of letting that delta x come to 0 and worrying about the line tangent to the graph, let's worry about the area subtended by that graph, or the area underneath that delta x. So here we've got z of x, here we've got z at x plus delta x, and we can form a little bit of a cuboid, what's it called, a rectangle, or it might be a bit off, could be a trapezium, but here we've got a bit of a rectangle here, and that rectangle has an area delta A. So there's delta x. That then is some height, and the distance between these 2 points is going to be something like delta z. So delta A is approximately equal to, because this is very, very close to being a rectangle, that delta A right there is very, very, very approximately equal to z of x times by delta x, right? Let's rearrange it. Z of x then is delta A over delta x. All of a sudden, if we change that from a finite change to an infinitesimal change, we look at what that area looks like as delta x gets smaller and smaller and smaller and smaller. Z of x then is the limit as delta x tends to 0 of delta A over delta x. So the function itself, z of x, is equal to the gradient of the area change under that graph. Z of x is dA by dx, where A is the area under the graph. So dz by dx is the gradient of the graph. Z of x itself is the gradient of the area under the graph. And so if derivatives and integrals are the opposite of one another, then we might say that the area is the integral of z of x. But before we get to that, we can say a function can be defined, instead of defining z of x as whatever this is, in terms of x. So this might be z of x equals x cubed, say. X cubed plus x squared plus 5. I don't know. We could define z of x that way. But equally, we could define z of x as the rate of change of area under the graph of the function. So that means there's something like an area function a of x associated with z of x that is effectively the opposite of its derivative, its antiderivative. Subtly different from integral, so we'll call it antiderivative for now. So let's imagine there's this area function. As x changes, so too will the area under the graph. As x changes, the area under that graph will get bigger or smaller depending on how x changes. So a of x is the integral of z of x. Z of x is the derivative of a of x. This right here is called the fundamental theorem of calculus. The proof that integrals, as defined as area under the graph, and derivatives, gradients of graphs, are effectively the opposite of each other is the fundamental theorem of calculus. It's proving that areas under graphs and gradients of graphs and graphs themselves are all related to one another. Super important. For a more concrete proof of this, have a look at this YouTube video. It's pretty interesting. But here's the basic understanding of it. So what we're going to do now is we're going to define something called a definite integral. So a definite integral is an integral defined specifically between 2 points on that graph. We've got x1 here, we've got x10 here. And what I'm going to do, just to make this proof a little bit more concrete, is I'm going to split it up into loads of those little rectangles. Each one has the same width, delta x. So that point there, z of x1, z of x2, z of x3, 4, 5, z of 10, z of x10 there. And so we see this is an alright approximation of the area under the graph. We've overestimated it here, underestimated it here, but generally this is an alright approximation. So the total area under that graph, this is what a definite integral is. It calculates the total integral under that graph. The total area is approximately equal to the sum of all of those delta AI's, right? So this is the area associated with z of x1. So z of x1 times delta x, z of x2 times delta x, x3 times delta x, z of x4 times delta x, 5, 6, 7, 8, z of x9 times delta x. It's the sum over all these segments. So that's what this symbol means. It's the sum from I equals 1 all the way up to n, where n is 10, of all of these segments. And so we can express that delta A there in terms of the function times by delta x, right? That's what we were just doing there. AT, total area under the curve. N is the number of segments that we're talking about. Let's now make this an infinitesimal change. So just like we did in the derivatives one, in the gradients one, we're going to make delta x smaller and smaller and smaller and smaller. As we make delta x smaller and smaller and smaller, if we keep x10 the same, then we're going to need more slices to cover that same distance. More and more slices. And as we get more and more slices, the amount we're wrong here, we've underestimated here and overestimated here, the more slices we have, the smaller delta x is, the more accurate is our calculation of the area under the graph. So when delta x tends towards 0, we'll get exactly the area under the graph. So the total area is not only approximately equal to, it is exactly equal to the limit as delta x tends to 0 of the sum from I equals 1 over all segments of z of x times delta x. Infinite segments, delta x is now equal to 0. We have an x1, and instead of x10, where n was 10 before, now we just say xf. It's the x at the end of that bit. That is now redefined as the integral from x1 to xf of z of x dx, where this integral is the opposite operation of the derivative, right? So if we were to differentiate a function, the integral would be the opposite of it. So if z of x was Cos, the integral of cos is sine, because the derivative of sine is cos. It's the opposite of it. So that's what this integral is. But what does it mean to do it between 2 points? Well, it means that we can calculate the total area from this area function a of x at this point. So we can imagine every bit of area that was ever under this curve all the way up to this point, minus every bit of area that was under this curve up to this point. And that's going to give us the difference, right? If we get all the area up to this point, minus all the area up to this point, then it's going to give us all the area between those 2 points. So the definite integral between 2 specific points gives us a number, almost in this case. It gives us an exact number, which is the area under the curve. Area function at the final point minus the area function at the start point. That's what that is. And we don't know what this area function is. This is just general, right? Z of x, the area function is just the integral of z of x. So we calculate it specifically at that point, take the difference, and that will be the total area. So that's a definite integral, where x1 and xf are constants in this case. But what do we do for an indefinite integral? So we've heard of definite and indefinite integrals before, probably, when you've done calculus at A level or in previous studies, and you'll know that definite integrals have limits, whereas indefinite integrals is just integrating and then adding an integration constant on the end, right? That's probably what you know. But why is that? Why is that? Well, let's keep this area function in our minds. Infinitesimal change. We're now going to say that the area function itself can be redefined as the integral between x1 and any point x we like of z of x. So that is now not a single value. It's a variable value. So there, look, x1 and x. So x can vary. X could be here, x could be here, x could be here. It's still the same integral operation though. We're just going to stick x in instead of a specific value. X is a variable. x1 is still a constant value though, because if we were varying both of them at the same time, that's going to get confusing. We're asking for trouble if we do that. Easier to just make one constant and vary the other. So because x is now a variable, a is now a variable, right? Here, in the previous one, that was the total area. It was a constant value. x1, x2 are constant values. That makes the area under this graph constant. But if x is itself variable, then the area of this graph depends on where x is. So x is now a redefined area function. We're now calculating a function. That is why it's called indefinite, because we haven't specified it to be a specific value yet. So that function we can calculate in exactly the same way as we did before. Calculate the integral, there's that area function in the middle, evaluate it at x1 and at this variable point x. So whatever this function is, stick x in and see what it looks like. What we're going to get is that the total area function is the area function minus some constant value. Let's redefine that minus constant value as the integration constant. And the total indefinite integral is the total area function plus some constant. And that is why an indefinite integral is called indefinite. It's because we don't know what specific endpoint it has. So this becomes a function with a specific constant attached. But now we have an intuitive understanding of what that constant is, right? That constant is this point here. It's where we start counting from. It's where we start our function from. Our area function can start here. And if it starts here, this integration constant is effectively every bit of area before that line, right? Because we're minusing off every bit of area before that point. If x1 was over here, then the constant would be different because it would be every bit of area below that point. That's what our integration constant really is. It's where we're starting this function, this area function. And so we can do any x we want, right? I can move x over there. Hang on, lost the graph. I can have x here, I can have x there, I can have x there. A of x is a function now, and it counts all the area under the graph up to the point x from the point x1, which is the integration constant. So that is the theory behind integration. Integration constants C are found by choosing specific conditions, effectively choosing where this area function starts. X is itself variable, so the area function changes. And if we want a definite integral, all we have to do is set that x to be a constant value, and it will give us the area under the curve between that point, and that's the definite integral. So the takeaway points, conceptually, it's all super interesting, I'm sure. But if you're not really interested in the concepts behind this or in the proofs behind it all I want you to understand is that rates of change are going to be important in physics because things change over time, and physics is all about proving how... It's about predicting how things change over time. So the derivative is the rate of change, and integration is the opposite of the rate of change. And because integration is defined as a sum, an integral is basically a sum of areas under a curve, then what we're basically doing when we integrate is taking the cumulative effect of many rates of change, one after the other. So if I'm driving a car and that my speed in that car is all over the place, if I'm accelerating in that car, then I want to integrate because I need to know how much distance I move whilst I'm moving at this speed, how much I move when I'm moving at the next speed up, how much I'm moving when I'm moving at the next speed up. It's not as simple as just taking the average velocity and timesing it by time. What I need to do is integrate, get the cumulative effect of all of those rates of change. That's what we're going to do in lecture 1 of the mechanics course. So the derivative of a graph at a point is the gradient at that point. The definite integral of a graph is the area under the graph between 2 points. The indefinite integral of a graph is the function describing that area, and the integration constant is where that function starts. Importantly, integral of a derivative with respect to a variable, integrating it with respect to that same variable, gives you back the same function plus some constant. Because when you take the derivative, you lose a bit of information. If you think about a graph, if I shift that graph up by a constant value or across by a constant value, its gradient isn't going to change. Up is a bit more obvious. If I shift it up, my gradient at that point x is not going to change, and that's effectively what my integration constant is. It's choosing where my graph starts. So integrating the derivative with respect to that variable gives you the same function back plus a constant. That constant tells me where I am on that area curve. So let's integrate some common functions. We're not going to prove it this time. It's literally just the opposite of differentiation. We've defined it to be the opposite of differentiation. So that means that if a polynomial has x of t is a t to the power n, then the derivative, you just bring the power down and take one off the power. So the integral of it is going to be, you add 1 to the power and then divide by the new power, right? So it's going to be the opposite operation. Instead of bringing it down first and taking 1 off, we add 1 to it first and then divide by that power. So add 1 to the power, divide by that power. And you can check that if I take the derivative of this, take down an n plus 1, it cancels with that n plus 1 and take 1 off, a t to the n, and the constant goes away, I get the same function back if I take the derivative of the integral. So these two operations are inverse because they cancel each other out. Exponential function, if I have a to the bt, I just bring that b down. So that means if I integrate, I need to take that b up, or in other words, divide by b. And we can see that if we take the derivative of this, that b will cancel with that b, get the original function back. A sine bt, you take that b out and change sine to cos. If I integrate a sine, however, I don't bring that b out, I again divide by that b, and cos and sine goes to minus cos. So if I integrate a sine function, I get minus cos. So it's a bit less obvious than these ones. If I integrate a sine function, I get minus cos. Whereas if I differentiate a sine function, I get plus cos. If I differentiate a sine function, I take that b factor out. If I integrate a sine function, I divide by that b value. And you can see from the cosine one, the opposite is true. So the derivative of cos is minus sine, and the integral of cos is sine. Same thing happens with that b factor. From these two, we can see that if I integrate sine and then differentiate that cos, they'll cancel out. Same for this. If I integrate that cos and then differentiate that sine, I'll get the same function back. So they're all inverse operations. So task 2, this is going to be integrating a constant. We're going to do this in the first mechanics lecture anyway, but let's just do it now. Scenario, you're given a constant value a. A is chosen not by accident, and you're asked to integrate it twice and observe what happens. So your tasks are to calculate the indefinite integral of the constant value a. I've called it v of t. Interesting. Use the equation v at 0 equals u to set the integration constant. So once I have v of t, which will be something plus c, I can say at t equals 0, v equals u. That's what this basically says. I can use that to set that integration constant. Then what I want you to do is calculate the indefinite integral of that new function v of t to get s of t, also not a coincidence, and then I want you to use the equation s at time 0 is equal to s naught to set the integration constant. So that should take you about 15 minutes, I reckon. So take 15 minutes, have a go at these questions. Right, that's 15 minutes, I reckon. Let's do this. Oh, did I not put the answers? There's the answers. Oh, that's in the wrong place. Hang on. That goes there. Nice. Right. Calculate the indefinite integral of the constant value a. A, constant value, is effectively a polynomial. It is a multiplied by t to the 0. T to the 0 is 1. Anything to the 0 is 1. So this is effectively a polynomial. Constants count as polynomials. So if I integrate a polynomial, I need to add 1 to the power and divide by the new power. So I've got t to the 0, so that's going to be t to the 1, and then divide by 1. Vt is equal to at plus c of 1. I've just called the integration constant c1 instead of c, so that I remember that it's specifically this integration constant. You don't have to call it c1, you could call it c, d, e, you can call it anything you like, but I tend to give my integration constant subscripts just so that I know what they are. And so now we can use that equation v of naught equals u to set the integration constant, right? Because if v of naught equals u, well, v of naught is a times naught plus c1, and that's going to equal u. So therefore c1 equals u, right? So we've got our new indefinite integral. V of t is equal to u plus at. You might recognize this as one of the Suvat equations or one of the constant acceleration equations. That's exactly what this is. This is where they come from. It makes a lot of sense, because if I now say v minus u divided by t, a change in speed over a time, that equals to an acceleration, right? So what we're doing here is starting with acceleration and integrating until we get speed. And from what we did in graphs before, we might now realize that u, the initial speed at t equals 0, is just where we happen to start our graph. We could have had anything we wanted here. I've said use the equation v of 0 equals u to set the integration constant. But I could also have said use the equation v of 8 equals b, say. You could have substituted this in and worked out what your integration constant must be. This condition is equivalent to me deciding where my graph starts. And you can do any condition you want as long as it's specific to the system that you're looking at. Usually, it's a lot easier to say at t equals 0, this is what it looks like. Or at position equals 0, this is what it looks like. So generally speaking, you won't have to worry about anything other than what happens at time t equals 0, because that's where it makes sense to start things, right? Set time t equals to 0 as the initial speed u. So speed equals initial speed plus a acceleration times time. That's what this is. So now we want to calculate the indefinite integral of our new function v of t. Because we've got a new function now, we can do the exact same process to get s of t. S is a shorthand for distance travelled. You could use d, but d tends to mean straight lines, so we use s to symbolise a path. Because it doesn't have to be a straight line. S could be some weird path. Nevertheless, the amount of distance we cover is equal to how our velocity changes over time. Cumulative effect of that is the integral. So s of t is equal to the integral of v of t dt. Let's do this. Integral of u plus at dt. U is a constant, so that does what acceleration did in the previous question. At, well, okay, that is a polynomial now, so t to the 1. Add 1 to the power t squared, divide by that power, 1 divided by 2, a half at squared, and we need that integration constant c2 to distinguish it from the previous one. So the integral of u plus at is ut plus a half at squared. Again, a famous Suvat equation, the second Suvat equation. And now what we want to do is use the equation s of 0 is equal to s0 to set that integration constant. So s of 0 is s0, s of 0 is u times t plus a half a t squared, t is 0, t is 0. C2 then is equal to S0. So hence, our full specified indefinite integral s of t is equal to ut plus a half at squared plus S0. So that's saying that the distance, or the position along the path that this is at time t, is where it started, plus the speed times the time, plus a half the acceleration times the time squared. That is how something moves under constant acceleration. The Suvat equations come from integrating constants. Nice. So if you did those questions, congratulations, you calculate the first two constant acceleration equations and understood where and why initial velocity and position values come from. Again, if you struggle bringing maths and physics together, remember you've already done it. Just like you did it for the vectors, you've now done it for the calculus questions. So no need to worry. Underneath all of the conceptual physics is mathematics. So task 3 is something I want you to do on your own time. You can do these after you've done them in maths if you like, or you can do them by looking up the chain and product rules, integration and substitution by parts if you want. Turns out that the chain rule and integration by substitution are related to one another. They're inverse operations again for combinations of functions. And the product rule and integration by parts are inverse operations as well. They're related for products of functions. And so task 3 is to use the chain rule to calculate dz by dx where there is a function z of y and a function y of x. So one thing you could do is just take y and substitute it straight in to get z of x, and then calculate z of x explicitly. But I think it's really useful to use the chain rule. So the chain rule dz by dx is dz by dy times dy by dx. Have a go at that and see whether or not the two methods agree with one another. Oh no, I just described the product rule. The chain rule is different to that. Don't worry about that. Do the chain rule whichever way you like. The product rule, dz by dx, is you differentiate the first, leave the second, plus leave the first, differentiate the second, and add the results together. So that's the product rule. You've probably done it before. If not, have a Google about it or wait till you do it in maths. But using the product rule, calculate dz by dx, where z of x is equal to this. like before, you could times these brackets out and then calculate explicitly with respect to x, but I'd suggest not doing that. I'd suggest using the product rule and comparing your answers, right? So differentiate the first, leave the second, plus leave the first, differentiate the second, and add the results together. Compare that with times in the brackets out and just differentiating it straight away. See what happens. Using integration by substitution, calculate the integral of z of x dx, where z of x is equal to x sine of 2x squared. So that one's a tricky one. It's quite tricky. Have a look up at integration by substitution and have a go at that one. And using integration by parts, which is the worst one. It's the hardest one to remember how to do it, but there's a guy on the internet called Black Pen Red Pen who has a really good method of doing integration by parts. So have a Google of that guy, Black Pen Red Pen. But using integration by parts, calculate the integral of z of x, where z of x is equal to x e to the 3x. Those are the 4 tasks. I reckon that'll take you about an hour. So have a go at that. I'm going to go through the solutions right now though. So take an hour, pause the video, come back to it. Using the chain rule, calculate dz by dx. Blah, 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 blah. The chain rule, dz by dx, is dz by dy, dy by dx. That's the product rule. Have I got these confused? No, that is a chain rule. No, I've got it right, I was getting mixed up. So yeah, dz by dx is dz by dy, dy by dx. Yeah. Yeah, of course it is. So we can do this explicitly by taking y of x and substituting it in as y and then calculating dz by dx explicitly. Or we can do dz by dx is equal to dz by dy, dy by dx and multiply them together. I reckon the chain rule's a bit more efficient, so we'll do it that way. So z of y, dz by dy is 2y plus 2, right? It's a polynomial, so we bring that power down and take one off the power, bring that power down and take one off the power, and the constant cancels. So dz by dy is 2y plus 2. dy by dx is 3e to the 3x, right? Because we just take down that prefactor of e to the x. So that means, according to the chain rule, dz by dx is this multiplied by this. 2y plus 2, 3e to the 3x. And it's good to not have any y's here, because we've got dz, z and x. We want this to be a function of purely x if we can. So let's substitute in e to the 3x there. dz by dx is 2e to the 3x plus 2, 3e to the 3x. Let's multiply. Let's pull out a factor of 2 there. And we've got 6e to the 3x, open brackets, e to the 3x plus 1. So that's good. Now, we're going to take that and use the product rule to calculate its derivative, right? So we're doing another derivative after it now. 2 derivatives in a row, double derivative. So let's use the product rule now. So the product rule, if I've got a function of 2 things, z open brackets, u and v, then if that function is u times v, then the product rule says that the derivative is differentiate the first, leave the second, plus leave the first, differentiate the second, add them together. And so here we can see that u is 6e to the 3x. We can define u to be that. And v is e to the 3x plus 1. So let's run the product rule. And like I said before, you can times these brackets out and do it explicitly, but let's do the product rule and make sure it works out. U of x is there. So du by dx is 18e to the 3x, because we bring down that power 3 times it by 6. 18e to the 3x. V of x, well, its derivative is just 3e to the 3x. Bring that power down, get rid of the constant. So now we can substitute everything in. Du by dx times v plus u dv by dx. Multiply all that and simplify it, and we find that dz by dx is 18, blah, blah, blah. It's this. So we just did the chain rule to take one derivative and the product rule to take the next derivative. And you'll find that if you take that first example and make it a function of x and take two derivatives, you'll find this is the answer. So that product rule and the chain rule are just shortcuts, shorthands, efficient ways of taking derivatives of functions and things like that. Becomes really important in circular motion, does the product rule and the chain rule, actually. So when we derive circular motion in about 8 weeks from now, it'll be super important. Integration by substitution, this one's quite tricky. So if I say z of x equals x sine 2x squared, I might want to say that u is equal to x squared, because x squared is kind of complicated, sine of x squared is kind of complicated, whereas sine of u, of a single thing, a little bit easier, we can deal with that. So now we take du by dx, right? We've defined a new function, u equals x squared. So du by dx equals 2x. And so if I make the very slight algebraic manipulation and say du, a little change in u, an infinitesimal change in u, is equal to 2x times an infinitesimal change in x, effectively timesing by the bottom of this fraction. That's not what we're doing, but it kind of is timesing by the bottom of this fraction. I can now take dx and replace it with 1 over 2x du, right? Integral of z of x dx is the integral of x sine x squared dx. Let's get rid of that dx and turn it into du. So it's a half 2 of x it's 1 on 2x du, and the x cancels. And x squared there is now just u. And all of a sudden we can solve this integral. Integrate it now. A half the integral of sine 2u du. Integral of sine is minus cos, and we divide by that 2, times it by this half. We get minus 1/2 cos 2u plus c. Substitute back in for x, and we get that the integral of z of x dx is minus 1/4 cos 2x squared plus c. And there we have it. Just a little bit of a note, if you calculate a definite integral, where we integrate by substitution, then when we change from x to u, we also need to change our limits to the equivalent u values. Because if you think about it, we're integrating here over x space. So these limits here are in terms of x, if there were limits there. So when we change to u space, we also need to change our limits so that they're in u space. So if x was 0, 0 squared, u is also 0. Whereas if x up here was like 4, if x up here even was 4, then u is equal to x squared. U would be 16, because we change our x limits to u limits instead. So that's integration by substitution. Check, differentiate the result using the chain rule and see if you get the right answer out. So you can use it using the chain rule because that's the operation that's the inverse of integration by substitution, it turns out. You can prove integration by substitution using the chain rule, or you can derive it from that. So differentiate this and check that you get the initial x sine 2x squared back. That'll be important. And the final one, integration by parts, right? So integration by parts says if you've got a function z of x equals du by dxv, then the integral of that function is uv minus dv by dxu. So the integral of du by dxv is uv minus the integral of dv by dxu. So this is the complicated one. It's a bit of a mess. It's kind of like the cross product was for vectors. It's the complicated one. It's the one where you've got to remember loads of weird stuff. But it turns out that integration by parts and the product rule are related to one another. So you can derive integration by parts from the product rule. So maybe that's one way of remembering it. But du by dxv is uv minus dv by dxu. So you kind of flip everything around. That is how we perform integration by parts. So here are the parts. Du by dx is e to the 3x. And u, therefore, is the integral of this. A third e to the 3x, right? We just divide by that prefactor there. V is equal to x, because it's the bit that's left over. So dv by dx equals 1. And so that's the bit that we want to make v in this whole thing. If we've got a polynomial in our thing that we want to integrate by parts, it's always best to set the polynomial to the v part, the polynomial to the bit that gets the derivative taken of it here, because that means we'll eventually get down to 1 and we'll be able to solve this integral exactly. So if you've got a polynomial, make sure that v equals the polynomial part of your integral, and then u, or du by dx, can equal the bit that's left over, and then you'll be able to solve it. So let's substitute all that in now. Integral of z of x is uv minus dv by dxu. So u times v minus dv by dx u. This is still an integral, but now it's something that we can actually integrate without doing it by parts. We can just integrate it, no problem. So let's solve it. This bit stays as it is, a third x e to the 3x. Integral of this, we just bring down another one of those powers. So now it's 1 over 9 e to the 3x. Simplify, we can pull that 9th out. We get a 9th. We can pull e to the 3x out. And what's left is 3x plus 1. Oh, that's not plus 1, is it? It's minus. Typo. There we go. Minus. That is a minus. That's a minus, because that's a minus. Minus. That is a minus. Take out a 9th. E to the x. 3x minus 1. Yeah, absolutely. So there we go. That's our solution of integration by parts. Differentiate the results using the product rule. So differentiate this using the product rule, because it's the inverse operation of integration by parts, and check that it gives you x e to the 3x back. If it does, you know you did your integration properly. And that's it. That's all I want you to know about integration. All I want you to know is that derivatives are important in physics because they let you predict what's going to happen down the line by looking at rates of change, and integration allows you to take the cumulative effect of all those rates of change and make functions as to what's going to happen in the future. So differentiation and integration are absolutely vital to physics because it allows us to make predictions of things going forwards. Everything else is just for interest and learning how to actually perform these things. So you probably had so much practice at A-level. Practice, practice, practice. But have another bit of practice using these examples. Do your trig functions, do your exponentials and your polynomials, just to get back in the habit before we start getting into the real complicated maths towards the end of semester 1. But until then, I've got some resources for you like I did last time. So that guy, 3 Blue 1 Brown, he also did a mad series on calculus. Super maths communicator. And he has moving graphics, kind of like what I did with GeoGebra, but a lot more dynamic, a lot more fluid, a lot clearer. He uses this great program. Because calculus is about rates of change, it's about things changing. And so if he can describe this using animations and things changing, then it's going to be a really, really good thing. So if you're interested in calculus, the real fundamentals of calculus and how different functions work, I strongly advise this video. It's really, really good. But that's the end of this supplementary series, so I hope you found it interesting. I hope you found it useful. Use it going forwards. But yeah, I'll see you in mechanics lectures. Thanks for tuning in.